We have always thought building design is so much more than just what a building looks like. DOHA Creative College is a new education facility providing international classes for 1,500 students from the age of 3 to 18. We don't want to just make a new building. We want to design a much more comfortable place for children and make it energy efficient as well. The project is located in Doha, Qatar, which is on the Arabic Peninsula. The climate there is extremely hot, and the average external air temperature can reach more than 30 degrees during the summertime. This is much higher than temperature that people feel comfy. The solar radiation is very strong, which can reach 190 kWh per square meter, and the duration of the average solar radiation is more than 11 hours per day. The challenge of this design is to protect kids from the extreme climate with energy-efficient technologies.
We started our design with typical courtyard plan. The courtyard is very suitable for the hot climate in Qatar, since it draws the cool air and circulated in the inner spaces of our building. It also provides an increased amount of natural daylight illuminating the classroom. Thus, changing our building orientation was important. We changed the direction to south-north orientation for maximum amount of uniformity of light. The next step was to extend it to meet our needs for building masses. This created a long courtyard that connects the whole building together. Lastly, we had three different masses. First one for the primary school, the second one for the secondary school, and last one for the shared community area.
The building site has no solar obstructions. The site is surrounded by two different roads. The buildings open to the community are located near to the main road to guarantee an independent access. Primary and secondary school buildings are located in the back to provide a safe environment for the children, connecting this building to the secondary road to separate the school from the general public. The design allows the public buildings to act as a noise barrier. Parking lot, green areas, and building shape act as a shield to provide safe and comfortable playgrounds.
Primary school have its own areas, including classrooms, specialist areas, and non-teaching areas. These areas are connected together, providing a safe and secure space for children. Same goes for the secondary school. The corridors separate our school classroom from the heat gain of the south facade, reducing the amount of energy needed to cool it. The gym, library, and catering areas are located in the same section of the building, away from the classroom, to provide private and noise-free areas. The pool and sports facilities are also separated from the main buildings, preventing noises and public users from disturbing the students from their educational studies.
The north facade has a glazing ratio of 34% to maximize the use of diffuse daylight. Glazing rate increases in the circulation as this area are shaded by other volumes. The south facade has a glazing ratio of 15% in the exterior wall to minimize the heat gains and direct solar gains. The interior wall has 25% glazing ratio to improve daylight conditions in the classroom. The corridor acts as a buffer area to control interior conditions. Our design allows cross-ventilation in all occupied spaces to use mixed modes when required. The northeast facade has a glazing ratio of 34%, protected by a dense cover of vertical shading elements. Finally, the southwest facade continues with the strategy implemented in the south to avoid direct sunlight.
As the solar radiation is pretty high, we designed horizontal shadings for the south window and vertical fins for the east and west facades. The length of the shading is calculated accurately to protect the whole window from March to November, to prevent solar gain from the glazing area. The shading is also designed to let the sunlight come in during the winter time to meet the heat demand.
The use of north facade skylight allows better luminance levels and light distribution.
The main material of the external wall is earth, which is a typical building material in Doha, with a low embodied energy. The external wall is designed with the U value of 0.26, and the double glazed window is also used to prevent solar gain from the envelope. The roof, which received the most solar radiation of the building, is designed with 250 mm insulation layer to achieve the U value of 0.15.
We run our building in Safira software simulation to see the expected performance result of our design. The consumption of our school building was 71 kWh per meter square per year, which is below the 2030 challenge by 2 kWh per meter square per year. Both lighting and equipment got about 24% of total energy consumption, while the cooling energy consumption dominated with 76% of total energy consumption, showing how important the cooling strategies in Doha climate. Moreover, we wanted to check our elements performance to see which elements have the greatest impact on heat gain. The most heat gain is happening in the north and south solar. You can decrease this with using better U values for windows and walls.
Using Sapphire software to simulate daylight conditions, we were able to identify 11% of upper-lit areas which are located in the south corridor as expected. The corridors protect the classroom from direct solar gains. 62% of the project is well lit, corresponding mainly to classrooms and other teaching spaces. Finally, the 27% under-lit area is divided in storage rooms, auditorium, and theaters that function with lower daylight levels.